Now we've talked a lot about sets and we've talked a little bit about applications of sets to Venn diagrams. And now we're going to apply set theory to probability. So this is going to be our introduction into probability. So a couple key terms to know when we're talking about probability. First is the sample space. So the sample space is the set of all possible outcomes for some experiment. And then an event is some subset of the sample space. Typically, there might be a specific event that you want to happen or that you don't want to happen, and it will be a subset of that sample space. And in order to determine the probability, you'll need to know the elements that are within the subset, so the event, and the elements within the entire set, so the sample space. Take a look at example 1. An ordinary die is a cube whose 6 different faces show the following number of dots: 1, 2, 3, 4, 5, and 6. What is the sample space of rolling a single fair die? Okay, so the sample space means what are all the possible ways that we could roll a single fair die? Well, since there are 6 different faces, there are 6 different possibilities. So our sample space is going to be 1 through 6. Now part B, list the elements of the event, so a subset, that the die shows an even number. So it's going to be some subset of the set that we just wrote down and just the even numbers. So that looks like it will be 2, 4, and 6. All right, take a look at example 2. An experiment consists of studying the numbers of boys and girls in families with exactly 3 children. Let B represent boy and G represent girl. Assume that we want to consider the order of the births. Okay, so we want to first start by writing the sample space S of this experiment. So we want to come up with all the different ways that we can have boys and girls with respect to the order of the births. And we're going to go ahead and list all those possibilities because we're writing out the sample space. So we could have 3 boys. We could have 2 boys and then 1 girl. We could have a boy and then a girl and then a boy. And then we could have a girl and then a boy and a boy. So in those last 3 cases I just mentioned, in all 3 cases there were 2 boys but 1 girl, but they were different because the order of the births matter. Okay, continuing on, we could have a boy and then 2 girls, a girl and then a boy and then a girl, 2 girls and then a boy, and then we could also have all 3 girls. Those are all the different possibilities that you could have if you have 3 children. Now, part B lists the elements of the event H that the family has exactly 2 girls. Now, it didn't say what order these 2 girls were born in, but we do know that they have 2 girls. So there are only some of these elements within the sample space that has exactly 2 girls. So not more than, not at least. So exactly 2 girls, it looks like it's when you have a boy and then a girl, boy, girl, or girl, girl, boy. So those are the 3 elements in this subset where the family has exactly 2 girls. All right, last one. List the elements of the event K that the 3 children are the same sex. Okay, so it looks like there are only 2 possibilities here. Either you have 3 boys or you have 3 girls. And so that is our subset of our sample space. Now we've talked about set operations, but we have not talked about set operations in the context of talking about probability. So let's say you have some set E and F be events for a sample space S. Now, we talked about E intersect F. That occurs when both E and F occur. When you have E union F, that occurs when E or F or both occur. Now that really is just the definition that you have already seen with set operations, but we're talking about events and we're talking about sample spaces. And then lastly, E prime occurs when E does not occur. So anything that's not within your set E. All right, take a look at example 3. A study of workers earning the minimum wage grouped such workers into various categories. which can be interpreted as events when a worker is selected at random. Consider the following events. E is that a worker is under 20, F that a worker is white, G that a worker is female. Describe the following events in words. Okay, so E prime, now E we were told is that a worker is under 20, so that means E prime is the opposite of that. That means the event that the worker is 20 or over, right? That's the opposite of being under 20 is being 20 or over. Okay, the next one, we have F intersected with G prime. So let's take this apart. So F is that a worker is white. G prime is that the worker is not female. So the intersection of those two means that both of those occur. So the event that the worker is white and not female. All right, let's look at the last one here. E union G. So remember that E union G means that E occurs, or G occurs, or both occurs. So in this case, E represents that a worker is under 20, G represents that a worker is female. So E union G represents the event that the worker is under 20 or is female. All right, mutually exclusive events are related to sets in that when we're talking about mutually exclusive events, it means that the intersection of E and F is equal to the empty set. You can also think of this as E and F being disjoint sets. That's a term that we've seen already when we've talked about set theory. All right, take a look at example 4. Let S equal 1, 2, 3, 4, 5, 6, the sample space for tossing a single die. Let E equal 4, 5, 6, and let G equal 1, 2. Are E and G mutually exclusive events? In other words, is the intersection of E and G equal to the empty set or not? Well, are there any elements that are common to both E and G? There are not, which means that yes, they are mutually exclusive because they have no outcomes in common. So in other words, E intersect G is equal to the empty set. All right, so now let's move into probability. So the basic probability principle is that if you have some sample space S with equally likely outcomes, and you have some event E as a subset of S, then the probability that event E occurs is going to be defined by this. So on the left here, we have the probability of event E, and on the right here, the N just stands for the number. So the number of elements in E divided by the number of elements in S. Now for any event E, the probability that E occurs has to be between 0 and 1. So at the very least, it cannot occur, so 0% of chance occurring. Or at the most, it has 100% chance occurring, so it goes all the way up to 1. All right, take a look at example 5. If a single playing card is drawn at random from a standard 52 card deck, find the probability of each of the following. Now I've put the standard deck of cards here on the right in case you're not as familiar with it. So first is, what is the probability of drawing an ace? Well, so the sample space is the 52 cards altogether, and then the event that we want to happen is to draw an ace. How many ways are there of that event occurring? Well, there are 4 ace cards, so that means there's a 4 out of 52 chance of that occurring, and you can simplify that and get 1 over 13. Do the same to draw a face card. So the probability of drawing a face card is going to be the number of ways that you can draw a face card over the number of cards in the sample space. So face cards are Jack, Queen, and King. We have 1 for each suit. So altogether, there are 12 face cards. So this will be 12 over the sample space, which is 52 cards altogether. And simplifying that, we get 3 out of 13. What's the probability of drawing a spade? So a spade, that's the second row there. how many ways are there of drawing a spade? Well, there are 13 spades altogether, and 52 cards in the sample space. And then simplifying that, we get 1/4. All right, what's the probability of drawing a spade or a heart? Well, how many different ways are there of drawing a spade or a heart? Well, we already know there are 13 ways to draw a spade. Right below that, those are the hearts. So there are 13 ways to draw a heart. So altogether, there are 26 ways of drawing either a spade or a heart, which means that this is 26/52. And then simplifying that, we get this is equal to 1/2. Now, a lot of the times with probability, we can come up with what we're doing here, which is the theoretical probability. But with a lot of real life applications, we're not able to come up with a theoretical probability. So what we have to come up with is what we call empirical probability. So in many real life problems, it's not possible to establish exact probabilities for events, but instead, useful approximations are often found by drawing on past experience. So here's an example. The following table lists the estimated number of injuries in the United States associated with recreation equipment. Okay, so something like this, you wouldn't be able to come up with probabilities unless you had information from the past. And you can use that information from the past to come up with probabilities, but you know that these are what we call empirical probabilities because we're using information from the past, we're using data in order to come up with these probabilities. Whereas with the cards, we know exactly how many cards are in the deck, and we know we can calculate the exact probability. We call that theoretical probability. All right, so in this example, find the probability that a randomly selected person whose injury is associated with recreation equipment was hurt on a trampoline. So we're trying to determine, out of all these different injuries from all these different equipment, what's the probability that if you randomly selected someone, that their injury had to do with being hurt on a trampoline? So we need to find two things. We need to find, well, how many injuries were associated with a trampoline, and how many injuries were there altogether. So on top, that's 107,345, right? Just simply looking at the number of injuries resulting from trampolines. And then on the bottom, you have to add up all the injuries, and all together, there are 903,887. And we'll simplify that, and that comes out to be about 0.1188, so about 12%. So the probability that you randomly select a person that had one of these injuries, the probability is that there's a 12% chance that you'll select someone who was injured on a trampoline.